The electric and magnetic fields are certainly measurable quantities in classical electromagnetism. We therefore expect that they should be similarly measurable quantities in quantum mechanics. But that suggests to us that each of them should have a corresponding operator, since it's through operators in quantum mechanics that we establish expectation values. The electric and magnetic field do indeed have operators associated with them. Let's look at how we can construct these operators and what properties they should have.
From the original definitions of the creation and annihilation operators, which we wrote in terms of Xi and d by dxi, we remember that we could write them like this, and now I'm putting in the index lambda, of course. So this was the creation operator and this was the annihilation operator. Now we note that we could write Xi lambda, now writing it as an operator, is 1 over root 2 times a lambda, the annihilation operator, plus a lambda dagger, the creation operator. We can see that directly from looking at these two relations here. Now, note that Xi lambda, we can write that as an operator. It always really was an operator, just as the original position r was really an operator. It's not just a coordinate, it's really an operator. So now we can write it explicitly with a hat on it. And as I said, we note that we can write it like this, as we deduce from these relations. Similarly, we can also write a dimensionless form of this generalized momentum operator, pi lambda. And remember, we defined that originally in this form here. Well, using the same relations and just adding them up the other way around, we can show that this pi operator is I over root 2 times the creation operator minus the annihilation operator. With these two definitions we've just written down here, we can now substitute back into our relations for E and B that define the mode's electric and magnetic fields. Instead of scalar quantities for the electric and magnetic fields for this mode, we now have operators. So I've substituted using all the correct algebra and constants, but for the P here using the pi operator, and for the Q here using the Xi operator, both for this mode, lambda. So the P operator, becoming the pi operator, brought in this difference of the creation and annihilation operators, and the Q operator brought in the sum of those two operators. Just as before, if we want to know the average value of a measurable quantity, we take the expected value of its operator. And the same is true here. For some specific state, which we might write as phi for this mode, we would have that the expected value of the z component of the electric field in this mode lambda, we would just find that by taking the expectation value of this operator for the field in that mode together with the state. So that's always what we did with operators. If we had an operator that corresponded to some physically measurable quantity, then to find the expectation value of that quantity, we merely evaluated a relation like this with the operator in the middle and the state that we were in on either side. And similarly for the magnetic field amplitude in this mode lambda, the y component of it.
This postulation of operators for the electric and magnetic fields is an example of a quantum field theory. We started out our discussion of quantum mechanics by quantizing the states of a particle. We've now come to a description in which we are quantizing a field, and we can view the particles, in this case the photons, as emerging from the quantization of the field. It's also possible and useful to construct quantum field theories for, say, electrons in a solid, for example, which gives a particularly elegant way of writing solid-state physics. Of course, much of modern quantum mechanics that's concerned with elementary particles is also in the form of quantum field theories. Such quantum field theories are therefore quite useful and rather profound. Having established these operators for the electric and magnetic fields, what other interesting properties might they have? we'll look at just one here, which is based on the commutator of the electric and magnetic field operators.
So let's look then at this commutator. With these field operators, we can work out this commutator. And we're now taking the commutator for the electric and magnetic fields. Explicitly, from these two relations that we had just worked out here, we can write down the commutator, and multiplying that out, all we really get here, we've got scalar quantities here and here. What we end up with is the commutator really of these two sets of operators here. Now we can multiply out this algebra, and a little bit of work to do the multiplication, but remember a commutator is this entity times this entity minus this entity times this entity. And if we work through all of that, we get all of these different products here. You can check them if you like. And those simplify down a lot. Most of them cancel out. And we're just left with these two here. But we know that this relation here was just minus this one here. And this one we recognize as our commutator, A dagger less A dagger A. And we knew that that equaled 1. So with our minus sign in front here, we've got minus 1 for this entity. So therefore, we can rewrite our previous result in this form here. And we have a commutation relation for the electric and magnetic field operators in this mode. Now, remember that every time we had a commutator that was non-zero, we could write an uncertainty principle. And for a relation that we could write in this form, the uncertainty principle would become this kind of relation. So the standard deviations then of the expected values of these two quantities are related. There's an uncertainty relation and an inequality here. And in this case, it's the electric and magnetic field amplitudes of this mode, and so they obey this relation. These field operators for the electric and magnetic fields do not commute in general, and as a result we get an uncertainty principle, which means we cannot in general simultaneously know both the electric and magnetic field exactly. This is a remarkable result, and we started off with a very different kind of quantum mechanics and things like position and momentum, which we believed had uncertainty principles. Now we've got to an uncertainty principle between two fields, the electric and magnetic field.